Hello everyone. We're starting a new theme in this lecture series, and in this theme we're looking at the properties of solutions. So of course a good place to start would probably be then by what do we mean by a solution? And simply put, a solution is a liquid with some solute in it, or differently put, something that has something else dissolved in it. And the reason why it might be interesting to look at this is when you add a solid to a pure liquid, then it changes the properties of that liquid. And as you will see as we progress through this theme, we will look at something called colligative properties, and that's just a broad term for all the kind of properties that change of a liquid once you add a solute to it. So in other words, all the properties of solutions that we will look at. But to get to that point, we must first, of course, look at units of concentration, because once you've dissolved something in a liquid, that means you start working with concentration units, because you will have one component, a solute, dissolved in a solvent, and hence you will need to know how much of a solute you have dissolved in that solvent, and how much you dissolved will dictate perhaps how much, or by what, how large, or to what extent the effect will be on the overall properties of the solvent. All right, so let's start there. So units of concentration. You should be aware of perhaps one or several of these at the moment. And the one that you most likely know is the one called molarity. Right. Notice it's molarity, and that's the one otherwise known with the big capital letter M, and it's the one where we say mole solute per liter of solution. So mole per liter, or we can just remind ourselves it's amount of solute, so mole of solute per volume of solution. So that is the concentration unit that we've introduced thus far, or looked at thus far. But there are other concentration units that we can also use. And the most confusing one probably is the one that sounds a lot like molarity, and it's one that's called molality. So notice the only difference is just an L there, so that's why I underlined it. And it's given a small m for, well, its symbol, and it's defined as the amount of solute per mass of solvent. So there are some similarities, but it is different in terms of, we'll look at how it's different from molarity just now. So in terms of perhaps just defining it in your mind, if you were to write it, you would say the mole of the solute divided by the mass of the solvent versus, so let's draw a comparison here. For the molarity, you would have said it's the number of moles of the solute divided by the volume of the solution. All right. So that's our first new concentration unit called molality. All right. So as always, you can just call it concentration. So you can call it a concentration. And it is the number of mole per kilogram solvent. And it has the units of mole per kilogram. All right, and that's mole solute per kilogram solvent. I'll also give it here. Cool. But how does that differ from one another? I have a little image here that perhaps assists us. So let's say, for example, you take the same amount of solute. So this is 0.100 mole potassium chromate. And you dissolve that in two different amounts of water. In the one case, so here on the right-hand side, we make up a solution that says make it up. We add enough water to make a 1 molar or a 0.1 molar solution. So here the concentration is 0.100 molar. In other words, the volume of solution equals 1.00 liter. All right, so you notice we added enough water to make up a solution of 1 liter, but that means the amount of water, the volume of water added, right, will be less than 1.00 liter. Let me move this a bit down. And you'll see why that is important in just a moment. Because on the left-hand side, what we did was we made up a concentration where we had a 0.100 molal solution. And do you notice what is the difference between these two solutions? Maybe the green will highlight that. Do you notice that the left-hand solution has more, or there's more of it, meaning that there's the volume, there's a difference in the level of the two flasks. And why is that? Because on the left-hand side, the water we added, so the volume of the water added, or let's rather put it in terms of if we're going to make a 1 or 0.1 molal solution, how much water do we need to add? We need to add 1 kilogram of water. And 1 kilogram of water is exactly 1 liter of water. So the mass of water we need to add is 1 kilogram. So that means the volume of the water on the left-hand side here is 1.00 liter. But what was it here on the right-hand side? It was less than a liter. Differently put, remember mass and liters here in this case at 25 degrees Celsius will essentially be the same. So on the right-hand side, the mass of the water here would be also less than a kilogram. And that's why there's a difference between the molarity and the molality. In the molality case, you use 1 kilogram of the solvent and you add that to the amount of mole that you want to make up. And then you get whatever you get here. On the right-hand side, you take the number of mole of your solute and you make up a solution to a specific volume. Right. Remember, you work with the volume of the solution. And now you can visually see that those are two different quantities. So, meaning that this is not the same, meaning 0.1 molal and the concentration of 0.1 molar does not result in the same type of solution because there's clearly, we dissolve the same amount of solute. So remember, this is our solute, the thing being dissolved, but the amount of water used to make these two solutions are clearly different. Okay, so all I actually wanted you to gather from this is those two concentration units are definitely not the same. Okay, right, so that's molality and molarity. Our next concentration unit that we will look at is something called mole fraction, mole fraction, and we give it with the symbol X. And basically what that is if you have a mixture of several things, then the mole fraction gives you the fraction of moles of that one component in the total mixture. Now, what do I mean by that? So consider you have like a little flask here, and I'm going to try and draw it quantitatively. So let's say you have a component A in black, you have a component B in red, so there's 3 of B, and then a component C, what's it, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3. You also have a component C in blue. Okay, and let's say the number of moles are equal to the numbers here. Then the question is, how many dots do we have in total? What is our total number of dots? You will agree that the total number of dots in this little drawing here are always 10, right? And how many of those dots is allocated to A? 4 of them, right? So NA is 4. So in principle, you could have translated this idea to mass. Let's say, for example, you had sodium chloride, potassium chloride, and cesium chloride, and you mixed that in some ratio. But you knew what the masses were, and hence you could translate that to number of mole. And you know what the number of moles were. You could get the total number of moles of your total mixture, and you still knew what the number of moles were of one of the components, say the sodium chloride. So in this case, it would be like the 4 here. So then basically what you do is you calculate what is the fraction that A is in this mixture. So you take Na and you divide it by the total. So that's what this equation tells us. It says you sum all the numbers at the bottom. So in other words, you take Na plus Nb plus Nc. So you say 4 plus 3 plus 3. That gives us 10. And Na is the fraction that we're interested in. So for this little example that I have here, it will be 4 out of 10. So in other words, its fraction is 0.4. Put differently, it means it's roughly 40% in terms of moles. It makes up 40% of the moles in the mixture, right? It's a mole fraction. It's the fraction of the moles allocated to A in the mixture. So now what's important about that? If we're looking at fractions, mole fractions, then all of the components in the solution must always equal 1. And why is that? If you look at all of them, so A is 4 out of 10, B will be 3 out of 10, and C will also be 3 out of 10. But if we sum all those numbers together, we must get 10 out of 10. We must get all of the number of moles in the total mixture. And that must then equal to 1. Okay. So the idea here is we must, whatever our mixture consists of, we want to get the total number of moles, and we divide whatever we're interested in, whether or not that be the species A, B, C, or D, and then we take that number of moles divided by the total number of moles, and that gives us a fraction. What is a fraction in principle? It's a percentage. Okay, and because it's a percentage, percentages always must be 100%, right? Or in terms of fractions, so fractions must equal to 1. Okay, so that's also a concentration unit. It's a mole fraction. So typically if you mix two things, so you have a solute in a solvent, then you only have two things. You have the solvent and the solute. So then it will be your solvent and your solute in some kind of ratio will need to give you 1. Okay, cool. Our next definition is weight percentage. So weight percent, same concept, I think, as a fraction or as mole fraction. I'm going to use the same analogy. In this case now, we just need to look at the masses. So let's say, for example, you again have 4 of this, you have 3 of B, and you have 3 of C. And you know what the mass is of A, you know what the mass is of component B, and you know what the mass is of component C, because you've made up a mixture of those 3 components. Then you want to know what is our weight percentage of, say, mass A. So that means we must take the mass of A, so mass of A, divided by the total mass, total. And we must remember that it must be multiplied by 100%. I forgot to add that in the equation. So add, multiply by 100%. So ultimately the equation should read MA divided by M total, multiplied by 100%. That then gives you the weight percentage of A. Differently put, what is the percentage mass of component A in the total mass? Okay, this one you should be kind of familiar with. If you have 2 things and you want to know what the percentage mass is of the one thing, you just take the mass divided by the total mass multiplied by 100%, right? And no matter how many things you have, then you just expand it for that. Cool. The final concentration unit, one that you might not have come across yet, is something called parts per million, and it refers to what you call relative quantities of your solute and your solvent. So it will always refer to 2 things, and it may be a bit difficult to do so. Let's first look at exactly the pure definition. So it's 1 part per million represents a solution that contains 1 gram of a substance in a sample with a total mass of 1 million gram. This is equivalent to 1 milligram of a substance in 1,000 gram. And what does that mean? That means, I'm going to write it like this, it means 1.0 gram of your, let's say, well, let's call it substance, plus 999,999 gram other stuff makes up a sample. Okay, that's what we're looking at. So you have 1 gram of something that you're interested in, a substance, and there is 999,999 gram of other stuff, and that together makes up one sample that weighs 1,000,000 gram. That is what 1 ppm. So this is 1 ppm. Okay. You can also write it as a ratio. So maybe if that helps a bit more. You can also write it as 1.0 gram substance per 1.0 times 10 to the power 6 gram sample. Okay, so it gives you a ratio. It tells you for every million gram of the sample that I have, I will have 1 gram of my substance. That is what the unit ppm tells you. And you can get other types of units of this as well. You can get in terms of just parts per million, you can get parts per billion, you can also get parts per trillion. Right, and billion is 10 to the power 9, and trillion is 10 to the power 12. Okay, so in other words, it just becomes the sample mass just becomes 10 to the power 9 grams, and then trillion is 10 to the power 12 grams. Okay, but every time it remains the same. So in other words, ppm gives you a ratio of it's so much substance. So let's say, for example, you were told it's 1 ppm lead in the water. So then it meant there was 1 gram lead per 1 times 10 to the power 6 gram lead plus water solution. Okay, so I hope that um, just at least gives you the ratio, so how you need to write it and how you need to see it. All right, we'll look at some examples in class where you need to just have these concentration units in place. Cool, I'll see you in the next video. Thank you for watching.